Good afternoon friends, once again to my channel, and this is lecture number 27 of physics optional paper 2. Okay, so we had learned up to the bra and ket notations in the previous class. Now we will learn about the measurements in quantum mechanics. Okay, we will learn about the measurements in quantum mechanics. Now there is always a term called as observable, which is seen frequently in quantum mechanics. So what is this observable? We will learn about that. But before moving on, if you are new to the channel in case, then I would suggest that you should watch the previous 26 lectures before coming to this 27th one. Okay, only then you will be able to understand the concepts better. Okay, or in case if you are already aware of all those things, then you can start from here itself, no problem. But in case you don't have any idea of the preceding concepts, then I would suggest to have a look at the previous 26 lectures, and then you may continue from here. Okay, the link of which is already there in the description as well as in the form of comments. Okay, so in quantum mechanics there is an observable. Okay, so quantity obtained by the process of observation or measurement on a physical system. There will be a physical system, quantum mechanical system, right? And we will make some observation on it. We will measure, for example, we measure the position, for example, we measure the momentum. Okay, so such things are called as basically your these quantities are obtained by the means of observation or measurement. We might go for some instrument in order to measure, and observation also we might make some observations with the help of instruments, our sophisticated instruments. Okay, so a quantity which is obtained in such a manner, such as momentum, position, energy, kinetic energy, potential energy, angular momentum, okay, spin, parity, all those things are basically your observable. Okay, so a quantity observed by the obtained by the process of observation or measurement on a physical system, right? These are observation and measurement on a physical system. Physical system means your quantum system. Okay, now unlike the wave function which might wave function psi, which might yield you sometimes this wave function psi might be complex also, right? I had already discussed this in the previous classes, that the wave function psi might be complex also sometimes, and in most of the situations in quantum mechanics in real life, the wave function psi is complex only. Okay, but your observables are never complex, they are always a real number. Okay, your observables are always real number. Okay, so some quantity will be there and there will be some unit associated with it. Okay, for example, if momentum is there, okay, if momentum is there, then the unit some number will be associated with it. For example, if I say momentum is 4 kg meter per second, okay, so 4 is the magnitude of your momentum and kg meter per second is the unit of your momentum. Okay, and accordingly you might calculate its dimensions also, m to the power 1, l to the power 1, t to the power minus 1, right? So these are the dimensions of momentum. So your momentum is also kind of observable. In quantum mechanics, such quantities are called as observables. Okay, now when we try to measure an observable, it basically disturbs your physical system as is written over here. Okay, so when we try to measure some observable, we try to make some measurements, it basically disturbs your physical system. Okay, disturb means, I had already told you in the previous classes that when we try to measure the position of an electron, we have to bombard it with photons. Okay, and while bombarding the electron with photons, some uncertainty in momentum comes out and some uncertainty in position comes out. Okay, so that is what is Heisenberg's uncertainty principle. So when we try to measure the position of an electron, we have to bombard it with photons. We have to put light on it, and light consists of photons. So photons make a considerable change in the momentum of the electron, right? So basically your measurement is disturbing the physical system. That is an example of measurement disturbing the physical system. Okay, so your electron is a physical system, and it is getting disturbed by the measurement we are trying to make. Okay, it is getting disturbed by the measurement in its position which we are trying to make. Okay, so it is basically disturbing its momentum also, right? So now the time is not an observable in itself. You must remember one thing in life of in quantum mechanical life. You must remember one thing, that everything depends on time. Your wave function psi also depends on time, right? I had told you that time dependent Schrodinger wave function. Okay, time dependent wave function or Schrodinger time dependent equation. So the wave function psi, it is denoted by capital Psi. The time dependent one, it is denoted by capital Psi, right? I had already told you this. So when it depends on time, it is denoted by capital Psi. So basically your observables will also depend on time. Okay, so but in Newtonian physics, what happens is we treat time also as an observable. Okay, in Newtonian physics we might take time also as an observable, as we will start the clock and stop the clock, and so we have observed the time also. In Newtonian mechanics it will work like this. But in quantum mechanical system, time is a universal parameter which determines everything. Okay, time is a universal parameter, as is written over here. You can see time is a universal parameter, and time is not an observable in itself. Okay, you cannot call that time is an observable. Time is a universal parameter to measure everything. Okay, everything will depend on time. Your wave function psi also will depend on time only. Okay, so it is a universal parameter on which everything else depends. So it is not an observable itself. It is a parameter to determine everything. It is a parameter to determine every other observable. It is not an observable in itself. Okay, time independent observables are also there in quantum mechanical systems, and time dependent observables are also there in quantum mechanical systems. Okay, so the time independent observables in the quantum mechanical systems are called as constants of the system. Okay, so what are the example of time independent observables? For example, your total mechanical energy for a conservative system, it may be constant, right? So it will be independent of time. Your mass, as we are taking non-relativistic motion, and we are also neglecting the spin of the particle, so time so your time mass is also time independent. So your mass is also constant of the system. Okay, similarly so it is written over here that time independent observables are called as constant of system. So examples are rest mass. Okay, as we are taking non-relativistic motion, I had already told you that Schrodinger developed his entire mechanics non-relativistically, right? Because the relativistic time the relativistic Schrodinger equation is basically your Dirac equation. It is no longer called as Schrodinger equation. We are calling it Schrodinger equation. That in itself means that we have ignored the we have ignored the variation of mass with velocity. We are taking non-relativistic. Schrodinger name in itself suggests that we have ignored the spin and relativistic variation of mass. Okay, so time independent observables are called as constant of system, and rest mass, charge of particle, etc. are constant of the system, constant for a system in Schrodinger wave equation. Okay, or in Schrodinger's quantum mechanical system. So rest mass, charge of particle are constant for the system, right? Rest mass is constant, charge of particles is a constant. Okay, charge of particle is a relativistic invariant also, right? Charge of particle is always a relativistic invariant, unlike mass. Okay, So there is no need to say that we are taking non-relativistic in case of charge, because charge is all invariant with velocity, but mass varies with velocity. But we will assume mass also as a constant of the system, because we are taking non-relativistic motions in Schrodinger wave equation. The development of Schrodinger mechanics is based on the assumption that spin is ignored, spin of any particle is ignored, quantum mechanical spin of any particle is ignored, and the motion is also non-relativistic. So rest mass and charge of particle are constant of system. Okay. Now there are some other observables. There are some other observables too, like position vector, momentum vector, total energy. Okay. So observables like position, momentum, total energy have the same meaning both in quantum mechanics and classical mechanics. So these two things like position vector, momentum vector, okay, total energy vector, have the same meaning. They have the same meaning in quantum mechanics as well as in classical mechanics. Okay. Now some of the observables might have the same meaning in quantum mechanics and classical mechanics. Some might have different meanings in quantum mechanics and classical mechanics. Some might be defined only in quantum mechanics, and there might not be any meaning. They do not have any equivalent in classical mechanics. That is also possible. Okay. So your position vector R, momentum vector P, and total energy E have the same meaning both in quantum mechanics and in classical mechanics. They have the same meaning. Okay. But observables such as spin, symmetry, parity, okay, these observables such as which have been written over here, that spin, symmetry and parity, they do not have any equivalent in classical mechanics. Okay. Now do not confuse this spin, symmetry. You might have learned about spinning top etc. in classical mechanics, but that spin and this spin is very different. This spin is quantum mechanical spin. We are not talking about the literal spin which is there in classical mechanics. In classical mechanics, when we talk about spin, it means that the object is literally spinning on its own axis. But our meaning of spin is very different here. It is quantum mechanical spin, not that absolute kind of spin which is there in classical. Okay. Absolute means really, literally it will spin. Really, in reality, it will spin on its own axis. But it is wrong to say that electron is spinning on its own axis. So the spin defined for quantum mechanical systems and microparticles, subatomic particles, the spin definition of spin is very, very different. Okay. So these things are defined, spin and symmetry, these things are defined only in quantum mechanical systems. Parity is also defined only in quantum mechanical systems. They have no classical analog. Okay. No equivalent in classical mechanics, or we can also say that no classical analog is there. Okay. No classical analog. Okay. No classical analog is there. Okay. So that is the thing which you should take care of. So now operator, we will talk about the operator. Okay. So mathematical rule or prescription. Operator is, what is operator? Basically it is your mathematical rule. Okay. To define something. Now we are moving on towards the operator. So in quantum mechanics, an operator when applied to a wave function gives corresponding observable quantity of the system multiplied by the wave function. So suppose I have an operator. Okay. So what work will an operator do? So suppose if I have an operator and I apply it on wave function psi, then I will get the value of observable multiplied by wave function. Okay. So such an equation will hold. Okay. Operator when applied on psi, wave function psi, it will yield you observable multiplied by wave function psi. Okay. So such is the thing which is there. Okay, so in quantum mechanics, an operator when applied to a wave function. Now when an operator is applied to a wave function, do not take it as a multiplication. Okay, I am writing like this does not mean that operator is being multiplied. Operator is being operated. Okay. And a result which you get is observable multiplied by the wave function. But over here it is not algebraic multiplication. I have applied operator on it. For example, when I say d by dx of x square, I do not mean so it is differential operator, right? It is differential operator. So I do not mean that d by dx is being multiplied by x square. I do not mean that d by dx is being multiplied by x square. It is not algebraic multiplication. I am applying d by dx operator on x square. So similarly, O hat operator, if I say over here, the O hat operator is being applied on the wave function psi. Okay. So that's the meaning of it. Okay. So in quantum mechanics, an operator when applied to a wave function gives the corresponding observable quantity of the system multiplied by the wave function, right? So such is the definition of an operator. Now I will illustrate this with the help of an example. You might have learnt about this wave function earlier, that psi x comma t means time dependent Schrodinger wave equation, right? Time dependent Schrodinger wave equation. So time dependent Schrodinger wave equation, the general solution of it might be written like this. Okay. So general solution of time dependent Schrodinger wave equation, the wave function which we obtain after taking its solution, it might look like this. So after it looks like this, take partial derivative with respect to x on both the sides. So after you take the partial derivative with respect to x on both the sides, what do you get? You will simply take the differentiation of it. Okay. Now partial derivative with respect to x is there. So as it is partial derivative, so time will be taken as a constant. So as time will be taken as a constant, what will happen to this? When you take its derivative, a will come out of the derivative symbol, and this exponential will remain as it is. And in addition to that, del by del x of this quantity in the power, del by del x of this quantity in the power will be multiplied. Okay. Del by del x of this quantity in the power, del by del x of this quantity in the power will be multiplied to this very expression. Okay. So I have basically applied just chain rule of differentiation. Okay. So after I apply that rule, I get del psi by del x equal to I px by h cut, I px by h cut a e to the power I by h cut x px minus et. Okay. Now this term once again means psi itself. So I will replace it by psi. Okay. So I replaced it by psi. Now looking at this expression carefully, what we obtain is that we might take this to the left hand side, this quantity to the left hand side, and after I take it to the left hand side, what do I get? I get something like this. Okay, which is given over here. And after I get it, I might go for multiplication in the denominator and multiplication by I in the numerator also. So after I get that, I into I will become minus 1 in the denominator. I into I will become minus 1 in the denominator, right? So minus 1 will come, and in the numerator I will come. So I h cut del by del x psi equal to px psi, right? Now you can have a look at it, careful look at it. I h cut del by del x psi equal to px psi, right? Now you have already learnt it, that I had told you that operator, I had told you general form, operator operated on psi is equal to your observable multiplied by psi. I had told you this form. So if you look at this carefully, then this is your observable, which is momentum along x direction, and this is your operator. Okay. So your operator is being operated on psi, and as a result you are getting observable px multiplied by psi, right? So this is the general form of it. So you got this. Now again, this thing, the one which has been written in the last, I h cut del by del x, I am repeating the same thing, but I am telling that h cut by I del by del x equal to minus I h cut del by del x equal to px hat. The observable which we are getting, okay, the observable which we are getting is this. The observable which we are getting is linear momentum along the x direction. We are getting this observable. So the corresponding quantum mechanical operator, this will also be called as linear momentum operator in x direction. What will this be called as? Linear momentum operator in x direction. Okay, this thing will be called as linear momentum operator in x direction, as when it is applied on psi, we are getting momentum in x direction. So it will be called as linear momentum operator in x direction. Okay, it will be called like that. Why it will be called like that? Because when it is operated on psi, we are getting momentum in x direction, right? So that's why it will be called like that. It will be called as a linear momentum operator in x direction. Okay, because it is yielding us the observable linear momentum in x direction, right? So this is basically your px cap. It will be represented by px cap, or it will be represented either by capital Px. Okay, so this is basically your operator. So what is it looking like? It is looking something like this. After I put the values over here, it is looking like px cap psi. Okay, it is capital psi. Basically it is looking something like this, right? So isn't it similar to operator applied on psi equal to observable multiplied by psi? Isn't it similar to this? Yes, it is very similar to this. So that's what I had told you in the beginning. Okay, so corresponding to px, that is the x component of momentum, we have this operator with us. Okay, so now we will learn about the various operators in the next class. Okay, up to here only we will learn in this class. In the next class we will learn about the various operators which are there in the quantum mechanics. Okay, so from here we will learn in the next class. Thank you very much. Jai Hind, Jai Bharat.